Okay, so we just defined the definition of a Taylor polynomial of degree n of a function at a particular point, c. And by definition, it is a polynomial that is characterized by, well, it has the same value at the point c, and the values of all the derivatives of the polynomial are the same as the first n derivatives of the function. A polynomial of degree n can't have any more derivatives beyond n, because use the power rule. So if you have a quadratic, the derivative of a quadratic is a line, the derivative of a line is a constant, and then take another derivative of a constant, you get 0. Whereas the function could have as many derivatives as it is. So the condition, so we have the n is important. The n says the degree of the polynomial, and it tells you how many of the derivatives agree, and the point c is important, and of course the function is important. So a Taylor polynomial requires 3 different things. You can't just say, here's a Taylor polynomial. You can't even say, here's a Taylor polynomial of a function. You have to say, it's the Taylor polynomial of degree 5 of the function sine of x at the point where x is equal to pi over 2. Okay, so there are these 3 different things that you have to specify when you're talking about a Taylor polynomial: the degree, the point, and of course the function. Now the idea is that you want to use the polynomial to approximate the function. And what does that mean? Well, that means, well, what do I mean by approximate? Well, we mean exactly the definition. So we want the polynomial to actually equal the function at that point, and we want that it has the same first derivative, has the same second derivative at that point, same third derivative up to n. So all the derivatives are the same up to n. But the derivatives are only assumed to be the same exactly at the point c. Okay, so that's what the definition says, and now let's give an explicit formula for these Taylor polynomials of degree n at x equals c. So again, there's a lot of things. So this whole thing is the polynomial that we're talking about. So the degree n Taylor polynomial of a function at the point x equals a. And now I'm using a instead of c because I'll be writing lots of parentheses. So here's what the Taylor polynomial looks like. So it's a polynomial of degree n. The constant term is given by f of a. The linear term is given by the derivative of a, in parentheses, times x minus a. So the only variable here is an x. All the other symbols that I'm writing down are actual numbers. A is a number, f of a is a number, f prime of a is a number. We're going to keep going. So right now there's only an x, so right now this is just a degree 1 polynomial, and you'll notice this is actually the same as the tangent line. F double prime at a times x minus a squared, and we divide it by 2 factorial, plus f triple prime at a times x minus a to the 3rd power, all over 3 factorial. And at this point, you can sort of see the pattern. So we just continue this out, and we stop when we get to the nth derivative at a times x minus a. This whole thing is to the nth power. That whole thing is divided by n factorial. So if you don't remember, let me just remind you in brief that this notation, n exclamation mark, in words that is said n factorial, and for our purposes n will always be an integer. So n is an integer, and n factorial is by definition you multiply n, all the numbers from 1 up until n. You just multiply them out. So you could write it in increasing or decreasing order because of the commutativity of multiplication. So for example, 3 factorial is just the number 3 times 2 times 1, that's equal to 6. 2 factorial is the number 2 times 1 is, of course, 2. 1 factorial is the number 1 which is equal to 1. And so because of this right here, observation, we can actually, if we wanted to, we could write this as a 1 factorial so that it looks even more consistent. Now all the terms look the same. And here's just a definition / notation, which is 0 factorial is actually defined to be the number 1. So 0 factorial is not 0. This is very important. So this is just a fact, a definition, or a notation. So in particular, you have to remember that 0 factorial is the same as 1, that we can actually write it like that. So when you write it like that, there's a very, very nice pattern. So let me rewrite all of these things together. So in other words, p of x, there's a nice symmetry. It is written as the 0th derivative of a function is just the function itself. And anything to the 0th power is just 1. So now you can see that all the terms actually have the exact same form. So that can make it a little bit easier for you to memorize this, because you'll need to memorize this formula. Well, then it just keeps going on forever. Not forever, it goes until you get to degree n. So you get the nth at a times x minus a to the nth power, all divided by n factorial. So you want to memorize, these are the same. So this is the explicit formula for the Taylor polynomial of degree n. And this you must memorize as soon as possible. So let's do some examples. So let's do something like, let's say f of x is, say, e to the x. So f of x is the function e to the x. We have to give you the function. We have to tell you the degree. Let's go out to, say, degree 4. And let's do it at the point where x equals 0, just to make our life a whole lot easier. Okay, so we're using this formula here. So a is 0. So the formula says that, I'll just write it out. So p of x will be, well, first I'll just write it, it's just going to be f of 0 plus f prime at 0 times x minus 0 is just x, plus f double prime at 0 times x minus 0 squared is just x squared over 2 factorial, plus f triple prime at 0 times x minus 0 to the 4th power, but that's just x to the 4th power, divided by 3 factorial plus f, and now I've got to use the proper notation, and I made a mistake writing and speaking. Okay, so sorry, that's the general form for the polynomial of degree n. So just using this formula here, applying it to this particular case. And so to fill in the details, now we just have to just do everything. But we know that this is a nice easy case. We know that if f of x is e to the x, then the derivative is e to the x. And in particular, all of the derivatives are e to the x. Fk of x is equal to e to the x. And so in particular, if you plug in 0, the kth derivative at 0 is e to the 0. And we know that e to the 0 is 1. So the degree 4 Taylor polynomial is, well, so this is, I'll just write it down. So this is e to the 0 plus f prime at 0. That's also e to the 0 x, plus f double prime at 0. That's also e to the 0 times x squared over 2 factorial, plus f triple prime at 0. That's also e to the 0. over x3 over 3 factorial, and the fourth derivative here is also e to the 0 x to the 4 over 4 factorial. So the calculation is just in blue over here. All of the higher derivatives of e to the x are e to the x. Okay, and of course e to the 0 is just 1, so that gives us 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial. So this thing is the degree for Taylor polynomial of e to the x at x equals 0.